Sujal Sukeja, can you hear me? Mukti Patodi, can you hear me?
Yes, ma'am.
Thank you. Good morning, all of you.
Good morning, ma'am.
Morning, ma'am.
So, last class we were dealing with VSEPR theory, shapes according to VSEPR theory. Now we are moving to bonding. Valence bonding, valence bond theory, VBT. How the bonds are formed between the atoms. Atoms are using their orbitals to form bonds. Hydrogen atom. These two hydrogen atoms come closer, come closer, come closer, and a bond is formed. So one hydrogen atom uses its valence orbital, that is oneness orbital, and the other hydrogen atom uses its valence orbital, that is oneness orbital. So oneness orbital of one merges with oneness orbital of the other. That is how this bonding is formed. We know that when this orbital containing electrons, they come closer to each other, they attract. At the same time, they repel also. Minus charges, electron repulsion. So attractive forces are there, repulsive forces are there, both are operating. When attractive forces become equal to repulsive forces, in the beginning when they are coming far away, only attractive forces overcome the repulsive forces. They attract. Repulsive forces are also there, but attractive forces overcome the repulsive forces. When this, as they come more and more attraction, repulsive forces as they come closer, repulsions also becomes more and more. Attractions are there, repulsions are there. When they are equal, when the attractive forces and repulsive forces are in equilibrium, we say a bond is formed between these orbitals. Oneness orbital of one hydrogen and oneness orbital of the other hydrogen, they merge and a bond is formed. Here, attractive forces and repulsive forces are in equilibrium. When we are making them, if they are made to come again closer, more closer, then repulsive forces will overcome the attractive forces. When the repulsive forces overcome the attractive forces, they repel. Means when the repulsive forces overcome the attractive forces, they repel and go far apart. So when in the beginning I said oneness orbital of hydrogen and oneness orbital of the other hydrogen, when they come from far away, attractive forces are more and repulsive forces are less. Their energy is decreasing and decreasing and decreasing and decreasing. When attraction is more, energy will be decreasing. Energy will be going down and down and down, and a stage will be reached. At the same time, repulsive forces becoming more and more. A stage will be reached when this attractive forces and repulsive forces are in equilibrium. Then we say these two hydrogen atoms are bonded. That is the lowest energy. The system is having lowest energy. Bond is formed. Lowest energy. If they are made to come closer again, that means repulsive forces overcome the attractive forces, then energy of the system will be maximum and they move far apart. Let's see with the help of a diagram. energy axis. This is the internuclear distance. Internuclear distance. Potential energy diagram. Potential energy diagram. In the nuclear distance, if the distance between these nuclei or these atoms that is more, that means atoms are far apart. These two hydrogen atoms are far apart. Far apart. So here let us see, this is the oneness orbital. This is the oneness orbital of hydrogen and this is the oneness orbital of hydrogen. When they are far apart, means only attractive forces are there. When they are coming closer and closer, their energy attraction becoming more and more. When they are coming closer, that's why they are coming closer. Attraction is more and more, that's why they are coming closer. At the same time, there is repulsion also. At that time attraction is more, so energy decreases. Energy decreases, 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 and it comes to a lowermost point. You cannot see it. Energy decreases and decreases, and the lowest energy is reached. At that time, attractive forces become equal to the repulsive forces. Now, that is the minimum energy. Attractive forces are in equilibrium with repulsive forces. That is the minimum most energy. We say a bond is being formed between these orbitals. So here, in the beginning, it was like this, oneness orbital, oneness orbital. Here, let us see this oneness orbital and oneness orbital very close to each other. When they reach here, that is oneness orbital merges with the oneness orbital of the other. Oneness orbital merges with the oneness orbital of the other. Right? This is oneness, oneness. So that is this point, and after that, if they are made to come closer, then here what we say, bond is formed, and this is the bond length, distance in the nuclear distance. This is the bond length. This is the bond length, and if they are made to come closer again, then the potential energy shoots up. Potential energy increases, and these particles move, these atoms move far apart. So this is the bond length. This is the bond length. So you write, this is the potential energy diagram for hydrogen. Potential energy diagram for hydrogen. So here you write 74 picometer. This is the bond length, 74 picometer, 74 picometer. This much distance, that is the bond length, 74 picometer. So this is the potential energy diagram. First they are coming from far away, coming closer, potential energy decreases, 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 and finally it is decreasing and decreasing and decreasing, and bond is formed here, 74 picometer bond length. Now attractive forces are equal to the repulsive forces. And when they are made to come closer, then the potential energy shoots up. That means these atoms move far apart. Okay, this is the potential energy diagram for the formation of H2 molecule. Now, from hydrogen atoms, molecule is formed. H2 molecule is formed. So atoms combine to form molecules by this overlapping according to valence bond theory. Valence orbitals are taking part. Draw this diagram. So orbitals overlap to form the bonds. You consider two atoms of hydrogen. This is this nucleus. This is atom A and this is atom B. This is Na, that is nucleus of atom A, and this is the electron of atom A. Electron of atom A. That is Nb. Nucleus of atom B, and this is the electron of atom B, Eb. What all interactions are there? Interaction means attraction or repulsion. What all interactions are there? You know that Na attracts this Ea. Similarly, Nb attracts this Eb. Nb attracts this Eb. So two attractions. Na, when they come closer, Na attracts Eb. So three attraction. Similarly, this fellow Nb attracts Ea. Four attractions. There are repulsive forces also. What are the repulsive forces? Na repel Nb. So that is one repulsive force. Four attractive forces we have seen. Now one repulsive force. Now Ea attracts Eb. Sorry, Ea repels Eb. Ea repels Eb. So two repulsive forces. So now when they are far apart, attractive forces are more than repulsive forces. That's why they are getting attracted and attracted. So they come, so there are attractive forces and repulsive forces. When these attractive forces become equal to the repulsive forces, then that equilibrium is reached, a bond is formed. So these oneness orbital and oneness orbital will be overlapping. In the case of hydrogen, overlapping is between oneness orbital, merging. They merge. Oneness orbital will be merging with oneness orbital of the other. In different atoms, not only 1s orbital in the valence shell, p orbitals are there. Maybe 1s orbital may be overlapping with the p orbital of the other. For example, hydrogen and chlorine. Hydrogen is 1s orbital, but chlorine is not 1s orbital. Chlorine's valence shell contains p orbital, p orbital. So these p orbital will be overlapping with s orbital. So what all types of overlapping, possible overlapping? Let's see what all types of overlappings to form this board. So next heading is overlapping of atomic orbitals. Overlapping of atomic orbitals. There are three types of overlap: positive overlap, negative overlap, and zero overlap. So write down overlapping of atomic orbitals. When two atoms come close to each other, when two atoms come close to each other, there is overlapping of atomic orbitals. There is overlapping of atomic orbitals. This overlap may be positive, negative, or zero. This overlap may be positive, negative, or zero. So we are going to see different overlaps. Positive overlap. Negative overlap. Zero overlapping. This is one p orbital. If it overlaps with another p orbital with its positive, a positive, negative. So positive, this is the phase sign. When the positive and positive, we said positive overlap. Suppose one is positive and negative, as in the case of one is positive, one is negative. Then it is negative overlap. This is called negative. Zero overlap means maybe one half is cancelled by the other half, or there is no overlap. That is zero overlap. So here, this is positive, this is negative. S orbital is always positive. S orbital, this is P, this is S. S orbital is always positive. So here, this positive overlap is cancelled by the negative overlap. So we call it as zero overlap. So that's about one. Now, positive, negative, and this is S orbital, this is P. So here again positive overlap, positive phase sign and positive phase sign. Positive phase sign means it shows it is the presence of electron density. And this is negative overlap. Now, by sidewise overlapping, this is in internuclear axis. Suppose perpendicular to this. So I am showing it like this. This is positive, this is positive. So perpendicular in this plane, or in this plane. So one p orbital, another p orbital. They are merging up and down. So that is positive overlap. This is negative overlap. Now in this case they cannot overlap because one is in this way and the other is in this way. One is standing this way and the other is standing this way. So no overlapping possible. So again, zero overlapping. So these are the different types of overlapping. Positive shows presence of electron density. So for positive merging, positive merging, positive overlap. Positive negative merging, negative overlap. Then here upper portion is positive and lower portion is negative. So cancel, zero overlapping. And here there is no overlapping. That is again zero overlapping. No overlapping in the sense this one is maybe in the y-axis and the other is in the x-axis. So they are perpendicular to each other. So no overlapping. And next is nature of covalent bonds. Suppose when they overlap, what type of bond is formed? What type of bond is formed? So, internuclear axis is taken as z-axis. Internuclear axis is, you can take any axis, x-axis, y-axis or z-axis. Internuclear axis is taken as z-axis. So this is z-axis. So this can be x-axis and this can be y-axis. All axes are mutually perpendicular to each other. Internuclear axis, this is z-axis. Okay, z-axis. So perpendicular to that x-axis, perpendicular to that is y-axis. You can take in any way, but generally, normally, we take internuclear axis as z-axis. So when they overlap, what types of bonds are formed? Nature of covalent bonds. Heading, nature of covalent bonds. You have got the portions for the term 1 examination, right?
Yes, ma'am.
Till what topic chemistry is there?
Chapter 4. Chemical
I'm first four set chapters.
Chapter 4.
Chapter 4 not.
First 4 chapters.
Chapter 4, it is not full. How much? No idea. Okay. Nature of covalent bonds. A. One S. So a bond formed here is called a sigma bond. Bond formed is called a sigma bond. So this is of hydrogen, this is of hydrogen. So we call it as H bond H. This bond is called a sigma bond. Sigma bond is shown like this. We write it as, this is SS overlapping by SS overlapping. SS overlapping. So a sigma bond is, this is called, this is along the internuclear axis only, Z axis. That is strong overlapping. Along the internuclear axis, there can be maximum overlapping. That results to a sigma bond. Sigma bond is a strong bond. It cannot be broken easily. If it is along the internuclear axis, maximum overlapping is possible. So strong bond is formed. B, sp overlapping. S orbital plus 1p orbital. For example, HCl. 1s orbital of H and 3p orbital of, on the third is the valential. So 3px or 3pz, Z takes Z as Z axis along the internuclear axis. So here we are getting like this one, positive, positive, negative, and between H and Cl, a sigma bond is formed. SIGMA, a sigma bond is formed. That is sp overlapping. Next, pp overlapping. Again, we are getting a sigma bond. You can take it along the Z axis, that is in the nuclear axis. So you will be getting a bond. You can say Cl and Cl. This is Cl, this is Cl. So Cl bond Cl, 3pz of each one, that is overlapping. So again, you are getting a sigma bond. Now, another type of bond, a weak bond by sidewise overlapping, that is called pi bonding. That is again pp overlapping only, pp sidewise overlapping, like this, like this, like this, like this. Positive, positive, negative, negative. So that is a sidewise overlapping, top and bottom. So here, this is the internuclear axis. So what you are getting, a sidewise overlapping, we call it as a pi bonding. Electron cloud will be like this. This is pi bond, a weak bond. But why it is a weak bond? Because it is not along the internuclear axis. We show it by like this. One is sigma. This pi is always formed along with the sigma. First sigma will be formed, then the pi will be formed. So one is sigma, one is pi. If a pi bond is there, you will see a double bond. For example, C double bond C H H, last year you learned. In that, this is a sigma bond between, means along the internuclear axis. That time, this pi bonds will be sidewise. So this is a pi bond.